Good morning, students. Myself, Dr. Eustace Russell, working as Assistant Professor, the Department of Mechatronics Engineering at Sri Muthukumaran Institute of Technology. Today, we are going to see about the subject called Kinematics and Dynamics of Machinery. Already, we have discussed three topics, three parts of the same unit, of Unit 1. We have discussed. Now, we are going to see the last topic of this Unit 1, that is cam derivatives. Cam derivatives in sense means that is a contours, cam contours of various motion, that is circular or circular cam and tangent cam. We are going to see the derivatives of those cams in these slides. That is circular, arc and tangent cams. Here we can see when the flange of the cam connecting the nose and the base circles are of convex circular arc, such cams are referred as circular arc cams. We can see both the sides we are having flanks. The blue color that is mentioned as a circular arc flank, and the tip part of this, that part is nothing but nose circle. That is a nose circle which is mentioned as a radius of this circle, nose circle, and this is again called as base circle, base one. You can see the base circle. Now this is this diagram give a mean dimensions of this circular arc cam. We can see this. What are the major part? Apex is the end part of the nose. That is the topmost portion of the nose. That is apex. Then that is flat face follower. That is touching with the base circle. So when the lifting part is will occur, the starting part of the circular cam, circular flank, whenever it is touching with the circular flank and moving towards the starting part of the nose, the follower will be raised gradually. When it is touching the end part of the apex, that is the nose part, at the time the follower will reach at the extreme position. At the extreme level it will reach. So now the cam that is given as a cam is rotating in a clockwise direction. The direction is also given. And the various angle is also given. That is a lift angle, that is alpha. And the flank lifting position, lifting stroke, that is taken as small d, that is given in the diagram. Now we'll see one by one the formulas, basic important formulas. That is expression for determining the displacement, velocity, acceleration of the follower when the flat face of the follower has contact on the circular flank. That is important. It's having a contact on the circular flank. We can see the contact only on the circular flank, not in the nose. Not in the nose. Only is the contact on the circular flank only. We can see R1 is nothing but OB. You can see in the diagram OB is nothing but least base circle radius. What is R2? Nose circle radius, that I already told. Capital R is nothing but QD. QD. That part is nothing but flank circle radius. QD. D is the distance between the center of the cam and the nose circles. Center of the cam, that is the D, as I already told you. D is the distance between center of the cam and the nose circles. That is from point O to P. Alpha is the angle of ascent. That is nothing but a lifting position. Whenever the follower is lifting, that is called as alpha. The angle of contact on the circular flank. Whenever we are having a contact from, that is what we can see means that is B2. That is B to D dash. At that point, we will be having an angle of contact on the circular flank. The displacement, here we can see the formula, x is equal to r minus 1 into 1 minus cos theta. This is basic formula. How we are obtaining means, what is BC? BC is nothing but this small area, BC. BC, how we are getting? OC minus OB. We are subtracting with OB. And we can write OC is nothing but, what we can write? That is DE. Because these two lines are parallel, we can write DE. And what is OB is nothing but R1, that is the base circle radius. Again DE can be written as QD minus QE. QD minus QE. We are subtracting that based on our simplification. We are doing these steps. In velocity formula is nothing but V equal to omega r minus r1 sine theta. We are using the derivative dx by dt equal to dx by dt theta into d theta by dt. Again, we are at the beginning of the ascent, starting position, the velocity will be 0 only. So there is no theta. Theta will be 0. It will be maximum when the follower just shift from circular flank to circular nose. When it is shifting position, at the time it will be very maximum. Velocity will be maximum point. That's why Vmax is equal to omega r minus r1 sine pi. Again, the derivative of acceleration dv by dt. In the above steps, we are using v equal to dx by dt. Here, change in velocity with respect to time. Again, we are using partial derivatives dv by d theta into d theta by dt. For our simplification, we are writing this. Then finally, we are getting a equal to omega square r minus r1 cos theta. These two formulas is very, very important. For maximum acceleration, minimum acceleration, we are using these formulas. That is omega square r minus r1, omega square r minus r1 cos phi. Now this is one formula. Based on the derivative parts, we are going to solve one basic problem. The problem represents the circular, symmetric circular arc cam operating flat face follower as the following particulars. Least circle radius is given 30 mm, a stroke that is given as 20 mm, angle of lift that is nothing but alpha 75 degree, nose radius 5 mm, speed is 600 rpm. These are the various things we are going to find. That is the principal dimensions of the cam. That is the various dimensions we have to find. Then the important step is acceleration of the follower at the beginning of the lift, at the end of contact with the circular flank, at the beginning of contact with the nose, and at the apex of the nose. These are the various calculations part we are going to find. Given data, R1 equal to 15 mm, R2 equal to 5 mm, 2 alpha equal to 150 degree. That is, we have to take 150 as half of the value, that is 75 degree. N equal to 600 revolutions per minute. Now this is the calculation. This slide gives the full glimpse of your of this calculation part. What is that? Total lift is equal to, total lift plus R1 is nothing but PO plus R2, that is 20 plus 30 equal to D minus 5, that is D equal to 45 mm. We are using this formula, R equal to this basic formula. Under the triangular rule, we are using this formula. By this, we can find the capital R by using the expression PQ equal to R minus R2 and QO equal to R minus R1. We can find the steps. We got the answers as 77.41 mm, 52.41 mm. Then again consider the triangle PQO. In this, PO by sine pi, which is equal to PQ by sine 180 minus alpha. Finally, we are getting pi equal to 34.2 degree. At the beginning of the left, what I already told, theta will be 0 only, because there is no lifting position, because 0. We are using the formula A equal to omega square r minus r1 cos theta. By using this expression and substituting those values, we will get 206.86 meter per second square. At the end of the contact with the flank, we will get theta equal to phi equal to 24 degree. Again, using with the formula, we are getting 171.09 meter per second square. At the beginning of the nose, we are having there will be under deceleration will happen. That's why this minus is given. Retardation. When it is reaching at the end position of the nose, there will be decrease in the acceleration, and followed by the apex of the nose. The same thing will be followed minus omega square d. Using this formula, you will be getting minus 177.7 meter per second square. So these are the two references which I have followed to prepare these topics. Kindly go through these slides, references. So it will be more useful for you. Thank you, students. Thank you for your kind attention for listening this part 4 of this video. That is unit 1. We have successfully completed. Kindly go through all the 4 parts of this unit 1. Please go through the video, subscribe the channel, and share this video to your friends. Thank you one and all. We will meet in the upcoming slide of the second unit.